In this video, we continue our discussion of Sturm-Liouville problems. We're going to start by reviewing some facts and results from the last video. The last video was really just discussing the problems in general and the necessary background to understand what the problems are. And we're going to review those concepts quickly. And if you need more detail, more examples of that, please watch the last video. I think it'll help you. After we review that, we're going to derive the Rayleigh quotient, and it's just a formula that will allow us to find the eigenvalues of a certain regular Sturm-Liouville problem. We don't tend to use that Rayleigh quotient, honestly. It's insightful if you are trying to solve, say, a lot of Sturm-Liouville problems, to have that formula and to be able to use it to come up with an expression that will give you some insight into the eigenvalues of your particular problem. But we're going to tend to solve problems from first principles. So after we discuss the Rayleigh quotient, we're going to solve some problems from first principles. Okay, so here are some definitions and facts that we need in order to work through these examples and actually make sense of them. So let's say chi is some space of functions defined on an interval I, and we have a linear differential operator L. Now, a couple of things. A linear operator is an operator that behaves like this. So if you take this operator and you apply it to a constant times a function plus a constant times a different function, this is what happens. You can basically take out that first constant and apply the operator to the first function, and then add that second constant times the operator applied to the second function. So for example, the first derivative operator, this d dx here, that is a linear operator, because if I take the derivative of 3 times f of x plus 4 times g of x, we all know from calculus 1 that that's just 3 times f prime plus 4 times g prime. And that is just this constant times the operator applied to the first function plus this constant times the operator applied to the second function. And that's exactly what that says here. This is more general, so that operator can be a little bit more involved than this first derivative operator. But if this is true for a particular operator, for any functions f1, f2 in our space of functions chi, and any constants c1 and c2, then we say the operator is linear. So, okay, so going back to this definition, we've got a linear operator, L, is a differential operator. So it involves differentiation as opposed to anti-differentiation or some other operation. If we've got an operator like that, and it's acting on functions in a space of functions chi, we say that that operator is symmetric on chi if the following is true. So if we take the integral of a first function times a linear operator applied to the second, minus the second function times a linear operator applied to the first, if we evaluate that integral for all functions f1, or any two functions f1 and f2 in the space of functions chi, and every single time we get 0, then we say that the operator L that's being applied here and here is a symmetric operator. And I think it's almost obvious why we call this a symmetric operator, because here we're applying L to F2, and then we've got an F1 over here, and here we're applying L to F1, and then we've got an F2 over here. If we exchange F1 and F2, we get basically the same thing. But yeah, it's the same thing in just the reverse order. So either way, we're going to get 0. So that's what it means for this operator to be symmetric. Okay, so we've got a linear differential operator that's symmetric on a space of functions chi. Now, another definition that we need to understand in order to understand what it is we're actually deriving when we solve a Sturm-Liouville problem is the definition of orthogonality of two functions. So we're going to let sigma be a function, and that function is defined on some interval I, if that function sigma is positive for all the x values in I. Then we're going to call two functions f1 and f2 defined on that I orthogonal with weight sigma on I if this integral is 0. It's just the product of f1 and f2 and sigma. If you evaluate that integral over I and you get 0, then those functions are orthogonal with weight sigma. Now, if sigma happens to be 1 all the time, then we just say the functions are orthogonal. Or if we're dealing with a set of functions, that are pairwise orthogonal. So for any two functions, f1 and f2, we always get 0. For all the functions in that set, we say that that function or that set of functions is an orthogonal set, which I think makes sense. Okay, so getting back to our goal, we want to discuss what a Sturm-Liouville problem is. Turns out to be a second order ordinary differential equation subject to some boundary conditions. It is a particular type of eigenvalue problem. So this is the definition of an eigenvalue problem. We want to let L be a linear differential operator acting on chi defined on some interval from A to B. Now, if we have an equation of this form, so you've got your operator applied to F plus a constant lambda, it's just a parameter lambda, times this sigma of X times F of X, if that is equal to 0. So that is a differential equation, and the derivatives are hidden in that linear differential operator L right here. We've got this differential equation for all X on the interval from A to B. If we have something like this, where lambda is a real parameter and sigma is a given function, and that sigma function, sigma of X, is always positive on the interval that we're interested in, we call this type of problem an eigenvalue problem. The numbers lambda for which the equation has non-zero solutions are eigenvalues. The corresponding solutions are eigenfunctions. Okay, so just let's go back to ordinary differential equations. This is just a differential equation. It's hard to tell what order it is because the order of the differential equation is hidden in this linear differential operator. So this is very general. This is just some differential equation that happens to have this particular form. Now, when we are looking at this differential equation on this interval, subject to all of these conditions that we've discussed, we call this an eigenvalue problem. And our goal in this is not just to find a solution to the differential equation, and it's not to find even a family of solutions to the differential equation. Our goal is to find pairs of things. So we're going to know the linear operator. We're going to know this function sigma. The only unknowns here are the functions, the solutions of the differential equation f of x. We call those the eigenfunctions, and the corresponding values of this real parameter lambda. We call those the eigenvalues. So our goal in solving this is not just to find the general solution of the differential equation, it's to find non-zero solutions to the differential equation, which are called eigenfunctions, that correspond to particular real numbers for particular values of this parameter, and those values of the parameter are called eigenvalues. So that's the goal. We've got a differential equation, and we want to find some functions that satisfy the equation for given values of the parameter. The parameter values are called eigenvalues, and the functions that satisfy the equation are called eigenfunctions. And of course, remember from ODEs, your ODE class, that a solution to a differential equation is just a function you could plug in that would satisfy the equation. So you substitute and you would get a 0 after simplification. Okay, now we're getting closer to discussing this Sturm-Liouville problem. Here's a very important theorem. So this is theorem 3.8. It says if the operator L in the eigenvalue problem is symmetric. As we discussed what symmetry means in this context, if the operator L behaves like this for all functions, f1 and f2 in the space of functions that we're interested in, then a few things are true. All of the eigenvalues, so those values of the parameter in the differential equation, are real numbers, and they form an infinite sequence, and that infinite sequence is increasing like this. As n goes to infinity, the lambda sub n go to infinity. And get this, the eigenfunctions associated with distinct eigenvalues are orthogonal with weight sigma on the interval from A to B. So we're going to have infinitely many eigenvalues. We don't just call them lambda, we call them lambda sub 1, lambda sub 2, lambda sub 3. For different values of n, we'll get a different value. And so we've got this sequence. So for each of those, we're going to have a solution to the differential equation f sub 1, f sub 2, f sub 3 that correspond to each of the particular eigenvalues. F sub n is the solution that corresponds to the eigenvalue lambda sub n. Those eigenfunctions are orthogonal. And again, remember what orthogonal means. It just means when we multiply them together and we multiply by sigma and we integrate over I, we're going to get 0. Okay. So when we solve these problems, we are looking for this list of infinitely many eigenvalues corresponding to the infinitely many eigenfunctions. And it turns out that those eigenfunctions are guaranteed to be orthogonal with this weight as long as the operator in our problem is symmetric. It's very important. If the operator is symmetric, all of this is true. Okay. Now there are a lot of conditions here, but I really want you to focus down here. We'll discuss the conditions. Those are generally satisfied. But this is just defining that regular Sturm-Liouville eigenvalue problem. So let's say we're interested in the interval from A to B. It's a finite interval. So we're not going from negative infinity to a constant, and we're not going from a constant to infinity. A and B are finite numbers. Let's say that P, Q, and sigma are real valued functions, and kappa 1 and kappa 2, and kappa 3 and kappa 4, they're real numbers. Now, we also need P to be continuously differentiable. So that means its derivative is continuous on the interval from A to B, and we need P to be positive for all x in the interval from A to B. The two functions, Q and sigma, they just have to be continuous. Their derivatives don't have to be continuous, but the functions themselves have to be continuous on the interval from A to B. And sigma is greater than 0 for all x in the interval from A to B. So that is, again, acting as the weight when we talk about orthogonality. Or orthogonality of the eigenfunctions, the non-zero solutions of the differential equation. Next condition says that kappa 1 and kappa 2 are not both 0, and kappa 3 and kappa 4 are not both 0. Okay, so provided all of that's true, here's your eigenvalue, a particular form of eigenvalue problem. We said over here, this is an eigenvalue problem in general. Some linear operator L applied to F plus lambda times sigma plus F, or times F, equals 0. Here's a particular one of those. This says take P, which is going to be given and it's differentiable, multiply it by F prime. Take that product and take its derivative. Then add Q times F, and then add lambda times sigma times F. And that will be equal to 0. Now I want you to notice that this piece right here is a linear operator applied to F. That's what that is. So this is a particular type of eigenvalue problem for this linear operator. The linear operator says, basically take the function, take its derivative, multiply by P, take the derivative of that, and then add Q times that function. Okay, so we've got a second order differential equation, and P will be known, Q will be known, sigma will be known. The only unknown here is F. That's the unknown function that we're trying to solve for. And it turns out we're going to look for infinitely many of those unknown functions, but those are going to be the eigenfunctions of our regular Sturm-Liouville problem. Now, there's one other unknown in this equation, and that's lambda. Those are parameters. Those are real values. Turns out there are going to be infinitely many of them. For each value of lambda, we want to find the corresponding function that satisfies the differential equation. And again, lambdas are the eigenvalues. The functions that satisfy the differential equation are called the eigenfunctions. And we've got these two boundary conditions. This one says that at the left endpoint of this interval, so we start at x equals a, we go to x equals b. This is at the left endpoint. We've got some constant times f, the solution to the differential equation evaluated at the left endpoint, plus a different constant, perhaps, or another constant, times the derivative of that solution at the left endpoint is 0. So this is just a relationship telling you how the function value and its derivative have to be related to each other at the left endpoint. When they say that kappa 1 and kappa 2 are not both 0, that's just saying that if they were 0, we'd have 0 equals 0. This is true all the time. If they're not both 0, we're going to have some condition on the left endpoint. So that's our first boundary condition. And the second boundary condition is similar. Kappa 3 and kappa 4 can't be 0 at the same time, because if they were, we just have 0 equals 0, which would tell us nothing. If they're not both 0, then we actually have some information about the function, the relationship between the solution to the differential equation and its derivative at the left endpoint. And that's given by this second boundary condition. So this differential equation, subject to these two boundary conditions, is called a regular Sturm-Liouville problem. And this is an ordinary differential equation subject to boundary conditions. So it's a boundary value problem. And our goal is to find the eigenvalues and the corresponding eigenfunctions that satisfy this equation. And then all of these things will hold for those eigenvalues and the eigenfunctions. The eigenvalues will be real. They'll form an increasing sequence. As n goes to infinity, the lambda sub n will go to infinity. And we're going to have eigenfunctions, f sub 1, f sub 2, f sub 3, that go with these lambda sub 1, lambda sub 2, lambda sub 3. Those eigenfunctions are going to be orthogonal with weight sigma on the interval from a to b. And that is just summarized in these two facts. Theorem 3.14 says that the operator in the left-hand side over here, which is the operator that looks like this, L applied to F gives us this. That operator corresponding to the space of functions that satisfy these two boundary conditions is symmetric on that space of functions chi. And 3.8 says that as long as the operator is symmetric, all of these things are satisfied. And corollary 3.15 says that the eigenvalues and eigenfunctions have the properties listed in theorem 3.8 because the operator is symmetric. Now, we haven't done a lot of examples of this in this video. We just talked through the results. If you want to see examples of this, if you want to make this a little bit more concrete and a little less abstract, a little less of a statement of facts, watch the last video. I think, and I hope that it will help you understand all of this in a bit more detail. Okay, so this is our differential equation. Now, if we wanted to come up with a formula for lambda, we could do the following. We could take this differential equation, multiply by f, and then integrate over the interval from a to b. When we do that, we come up with an expression that we can solve for lambda, and that equation that defines lambda is called the Rayleigh quotient. Okay, so we're just taking this again, and we're multiplying it by f, and then we're integrating. So we're going to integrate from a to b. So, and I'm going to drop the dependence on the x, but I think we all remember that these functions depend on x. So we'll have p times f prime plus q times f plus lambda times sigma times f. We want to take that equation and multiply by f and then integrate. So multiply by f. F times f is f squared. Now this was equal to 0. So when I multiply the 0 by f and integrate, I still get 0. So that's true. Now that is equivalent to this statement. I could separate this into a couple of different pieces. And again, I'm interested in solving for lambda. So I've got f times p f prime plus q times f squared. And then I'll just factor out the lambda. That's just a real value constant. You've got that right there. And this expression can be written in a different way. This expression is related to the derivative of P times F prime. So let's look at that. Just by the product rule, if we do the following. This is what we get. If I take the derivative of F times F prime times P, using the product rule, if this is my first function and this is my second function, I would have derivative of the first, and I'm just going to switch here from the Leibniz operator notation to prime notation. It's derivative of the first times the second, plus derivative of the second times the first, now, if I apply this, the product rule to this again, this being my first function this time and this being my second function, we'll have derivative of the first times the second plus derivative of the second times the first. And of course, F prime times F prime is just F prime squared. So we've got F prime squared times P plus F times F double prime plus P prime times F prime. So we have that right here. Oops. Now I want you to compare that to this. If I just expand that expression right there, I've got F times P F prime prime. By the product rule, the derivative of this piece is derivative of the first times the second plus derivative of the second times the first. I end up with P prime F prime plus P F double prime. Now I've written them in different orders, but notice that this expression is equal to this and this expression is equal to that. And I've got a P F double prime right there and right there. And I've got a P prime F here and also here. So the only thing that these two do not have in common is this piece. So if I want to, I can put these two pieces together. This right here can be replaced by this. So if I'm trying to solve for this, it's just going to be the derivative of this product of three functions minus that. So putting these two pieces together, we've got F prime P, that whole product prime is equal to F prime squared times P plus this expression, which is the same as, oops, this expression. And if I want to get this by itself, I just subtract this from both sides. And if you're saying to yourself, why would we do that? It's because we would love to have this in our integrand somewhere, a function raised, or a function's derivative, because then when we take the antiderivative, we just get the original function. So it just allows us to simplify that expression that we've written at the top a little bit when we choose to evaluate those integrals. Okay, so we're going to take this right here and we're going to make a replacement. It's just a substitution. And then we'll have this. So going back to our original line of reasoning. Oops, I want to go to black. We have this. The original, we have the integral from a to b of this, which is equal to this, plus lambda times the integral from a to b of sigma times f squared dx equals 0. Okay, now the Rayleigh quotient is an expression for lambda. Now we'd like to be able to get lambda by itself. We're not guaranteed to be able to get lambda by itself unless this is non-zero. But remember the conditions for the regular Sturm-Liouville problem. Sigma of x is supposed to be positive for the interval from a to b. So this is strictly positive. And the function f is an eigenfunction of our differential equation. Now remember, eigenfunctions are non-zero solutions to this differential equation. Well, in general, there are non-zero solutions to this differential equation, some linear operator, but we're interested in regular Sturm-Liouville problems. So eigenfunctions, the ones that we're interested in, are non-zero solutions to this equation. If they're non-zero and we square them, they're definitely positive, or that function squared is definitely positive. So I've got a positive function times a positive function. I'm integrating from a to b. So that means that this coefficient right here is positive. And if this is positive, I can solve this expression for lambda. So let's get lambda by itself. In order to do that, we can subtract this expression from both sides and then just divide by this. Excuse me. In order to do that, I think I want to simplify this expression a bit. Or before we do that, I want to simplify this a bit. I've got the integral from a to b of this product, the product's derivative. The antiderivative of this would, of course, just be that product. So we will write, and I think I'm going to write it in the reverse order, p times f prime. The antiderivative of this is this, and then we would evaluate from a to b. Now, typically, the way the Rayleigh quotient is written, we factor out the negative from here. So we've got a negative times the integral from a to b of, get p times f prime squared minus q times f squared dx. And remember, p is a given function, q is a given function. The only unknowns here are f, which is just a representative eigenfunction, and lambda, the representative eigenvalue. Because we are dealing with a regular Sturm-Liouville problem, this expression, this integral is strictly positive, and we get the following. Lambda is equal to this. Now, in order to get this expression by itself, we're going to subtract this from both sides and add this to both sides. Eventually, we'll get this in the numerator over here on the right-hand side. And we're going to take all of that and divide by this guy in order to get lambda by itself. Excuse me. Now, I don't tend to use this, honestly. We're going to find the eigenvalues and eigenfunctions from first principles. I don't believe in deriving formulas and then just plugging things into the formulas and sort of doing a plug and chug thing to figure out what the lambda values should be. We're not going to do that here. But we can sort of plug and chug to infer some of the characteristics of lambda before we actually solve a Sturm-Liouville problem. And I think that's what we'll do in our first example. And then we'll work through the second example, and we won't necessarily use this formula. So here is our first example. We want to find the eigenvalues and eigenfunctions of the regular Sturm-Liouville problem. We'll just abbreviate that S-L. And here's our problem. We've got f double prime plus lambda times f equals 0, and f of 0 equals 0, and f of L equals 0. Now I want you to compare that to this, that pf prime prime plus qf plus lambda times sigma times f equals 0 for x between a and b. And this is for x between 0 and L. And kappa sub 1 times f of a plus kappa sub 2 times f prime of a is equal to 0. Kappa sub 3 times f of b plus kappa sub 4 times f prime of b is equal to 0. This is a regular Sturm-Liouville problem. We have a second derivative of f right here, so that means our p is just 1. There is no just function times f over here that's not associated with that lambda, so q is 0, and the lambda sigma f term is just lambda f. So that means sigma must be 1. So this is 1, this is 0, this is 1. Now notice we don't have any derivatives in our boundary conditions. So that just means that kappa 2 and kappa 4 are both 0, and kappa 1 and kappa 3 are both 1. And instead of a and b being the endpoints of our interval, in this case, we're saying that x equals 0 and x equals L are the endpoints of our interval. So this is a regular Sturm-Liouville problem associated with those values of p, q, lambda, kappa 1, kappa 2, kappa 3, and kappa 4. Now, if we just focus on the values of p, q, and sigma, and then we substitute those into our Rayleigh quotient, we can infer some qualities, some properties of the eigenvalues for this particular Sturm-Liouville problem. So if p is 1 and q is 0, lambda is going to be equal to the interval from a to b, so that's 0 to L in our case. If p is 1 and q is 0, this is just going to be f prime squared times dx. And then over here, if I evaluate that evaluate this expression at 0 and L and subtract, well, since f of 0 is 0 and f of L is 0, this whole piece will be gone. Let me just show that. In our case, p is 1, so I can say that. So we're going to have f of L, oops, that prime shouldn't be there. F of L times f prime of L minus f of 0 times f prime of 0. And because of our boundary conditions, I've got 0 times something, which is 0, and then 0 times something else, which is 0. So that piece is 0. So this piece is gone. And then in the denominator, we'll have the integral from 0 to L of 1 times f squared. One thing I want you to notice is that this integrand is certainly positive, or possibly 0. So that just looking at this, we can tell that lambda would have to be greater than or equal to 0. Of course, the denominator is always positive. Because again, we're talking about eigenfunctions. Those are solutions to the differential equation over here. Those are non-zero solutions to that differential equation that correspond to these particular values of lambda called the eigenvalues. Since those are non-zero solutions, f squared is certainly positive, and that means that integral is certainly positive. So we can just look at this and tell that this would have to be a greater than or equal to 0. But notice that the only time that this would equal 0 is if f prime is equal to 0. On the interval from 0 to L. But f prime equals 0 would imply that f is equal to a constant. And if f is equal to a constant and f of 0 is equal to 0 and f of L is equal to 0, so we're on the interval from 0 to L, and we're dealing with a constant function, y equals f of x that passes through this point and this point, well, the only constant function is the zero function. But that contradicts the fact that we're talking about eigenfunctions. Eigenfunctions are non-zero solutions to a differential equation. And I'll write that down. F is an eigenfunction. So F cannot be zero. What does that tell you? It tells you that lambda equals 0 is not a valid eigenvalue of that differential equation. So it's not an eigenvalue of this regular Sturm-Liouville problem, which is a differential equation subject to these boundary conditions. Okay, so now we know that lambda equals 0 doesn't work. So that means we know that all the lambda have to be positive. Given that we know that all the lambda have to be positive, we can just look at that case. Let's solve the equation now, or solve the boundary value problem now. Now, one thing that I want you to notice is that we got all of that from just this expression, and we got that expression from manipulating the original differential equation, multiplying by f, integrating, and then solving for lambda. And we know that we could do that based on the properties of the functions from the regular Sturm-Liouville problem. And we substituted directly into the Rayleigh quotient. I want you to notice or know or that we generally don't do that. We generally don't just derive formulas and then plug things in. You might do that if you're solving a lot of problems like this, but if you're in the partial differential equations class, I bet you anything your PDE professor is going to want you to solve these problems from first principles. So if I were to solve this problem, this boundary value problem from first principles, I might not know immediately that lambda has to be strictly greater than 0. It might not be obvious to me at all that lambda, in this case, for this particular Sturm-Liouville problem, the lambdas have to be greater than 0. All I know from our original problem statements and original background is that we have infinitely many real eigenvalues, and they form an infinite increasing sequence like this. So there would not really be any guarantees that this is a strictly greater than 0. The lambdas are greater than 0. You would usually just look at all possible cases. And usually we look at the cases where lambda is positive, negative, or 0. That actually all deals with, or is all related to trying to solve this differential equation. Okay, so having said all that, let's solve the differential equation from first principles. We already know because of the Rayleigh quotient that the lambdas that will work are going to be those that are positive. But let's pretend we don't know that. In that case, I would look at this on a case-by-case basis. So I want to solve this differential equation. It is a second order differential equation, and lambda is a real parameter. So this is just a homogeneous constant coefficient differential equation. And I might be interested in when lambda is negative, when lambda is positive, and when lambda is 0. Now, if you're saying to yourself, why would you care about those three cases? Well, we care about those three cases because the forms of the solution tend to be different based on the value of lambda. We're going to have the same characteristic equation for this homogeneous constant coefficient ordinary differential equation, but the form of the solution looks different if that lambda is positive, negative, or 0. So let's look at the three cases. Let's think of lambda as negative. So if lambda is negative, then lambda is equal to, let's say, a -1 times lambda, let's say star, where lambda star is positive. That's going to allow me to solve this in terms of lambda star, a positive value of the parameter. So then we'll look at the differential equation. Replacing lambda with lambda star, I've got this. And notice again that this is a homogeneous, linear, ordinary differential equation with constant coefficients. Now back in your ODE class, you learned how to solve this by letting the function that you're looking for, in our case f, be equal to e to the mx. We said if we've got a constant coefficient equation, it makes sense to expect solutions in this form. We just need to find the values of m that cause this equation to be true. So we will take the first and second derivative because it's a second order equation. Get m times e to the mx and m squared times e to the mx. Then if we go back to the differential equation and substitute, we'll have m squared e to the mx minus lambda sub star times f, which was e to the mx. That's going to equal 0. And then we factor out the e to the mx. Now that exponential function is always positive. So that means m squared minus lambda star is equal to 0. And that means the following. M squared is equal to lambda star. And that means that m1 and m2 are equal to plus and minus the square root of lambda star. Now, lambda star is positive. So these are two real numbers. That means our two linearly independent solutions to the differential equation are f sub 1 is equal to e to the positive lambda square root of lambda star times x, and f sub 2 equals e to the negative square root of lambda sub star times x. And remember, again, we're just taking the m1 and m2, the two real values that we found, and we're substituting those into the form of our assumed form of the solution. Now, one thing that I want you to notice is that these are exponentials that look almost identical, but this exponential has a negative coefficient and this one has a positive coefficient. Now, remember, back in Calc 2, you learned about this. Calc 2 or Calc 1, depending on your institution. We learned about the hyperbolic sine function. We said that hyperbolic sine of x is 1/2 times e to the x minus e to the negative x. And we said that hyperbolic cosine of x was 1/2 of e to the x plus e to the negative x, remember? Now, notice that those are just combinations of these two functions, but instead of an x, I've got a square root of lambda sub star times x for here, here, and here. So if I wanted to, I could, instead of using these two functions as my two linearly independent solutions of the differential equation, I could come up with two different linearly independent solutions involving the hyperbolic sine and hyperbolic cosine functions. You're saying to yourself, why would I want to do that? It's just because it makes the differentiation and like the simplification of the solutions to the boundary value problem a little simpler. Instead of dealing with exponentials, we're dealing with hyperbolic sine and hyperbolic cosine functions. The calculations are going to be nice and easy. So if you're wondering, how can I be guaranteed that these two functions are solutions, or a variation on these two functions are solutions to this original differential equation, given that we know that these are two solutions to the differential equation? Remember also from the ODE class that if you have two functions, y1 and y2, and those are solutions to a homogeneous differential equation. And it has to be a homogeneous linear ordinary differential equation. Remember that we were guaranteed that a constant times the first function plus a constant times the second function is also a solution. We learned that, we studied that back in the ordinary differential equations class. Now, since that's true, that means since this function is a solution and this function is a solution, then the hyperbolic sine of square root of lambda sub star times x, which would be 1/2 of e to the square root of lambda sub star times x minus e to the negative exponent there that we derived. That's just 1/2 of the functions f1 minus f2. Or if you prefer, you can distribute that 1/2. So we've got that right there. So the hyperbolic sine function is just a linear combination of these two functions. It's this particular linear combination of those two functions. So since these functions are solutions, this function is a solution to the differential equation. Similarly, the hyperbolic cosine, that's going to be 1/2 of the first function plus the second function. So we could use these two linearly independent solutions to form our general solution to the differential equation. But in this case, it's going to be helpful to use these two solutions as our two linearly independent solutions to the differential equation. So we'll call this F1 and that F2 if we want to, or we will just write down the general solution of the differential equation now. It's a constant times the hyperbolic sine of the square root of lambda sub star times x plus a constant times the hyperbolic cosine of the square root of lambda sub star times x. All right. Now, I'm not looking for a general solution to a differential equation. I'm looking for solutions to a boundary value problem. So looking at the case when lambda is negative, and we found the solution to this differential equation in that case would involve hyperbolic sine and cosine functions. It's one way to write it. And now we want to find the values of those coefficients that will satisfy these two boundary conditions. First, we have f of 0 equals 0, and the second condition is that f of L is equal to 0. So we'll replace x with 0. Let's plug in 0 here. And then remember from calculus 1 or 2, wherever you learned about hyperbolic functions, that this is 0 and that's 1. So we're just going to get C2 there. And we're told that f of 0 is equal to 0. And we also know that f of 0 has to be C2. So we set that result equal to 0. And then typically we would have a relationship involving C1 and C2. This one's really simple. This one just tells us that C2 must be 0. Okay, so we know that C2 is 0. So this term is gone. Now we also know that f of L has to be 0. So that means when I replace x with L, I'll have C1 hyperbolic sine of the square root of this lambda sub star times L. And we need to set that result equal to 0. Now, the only way that product is 0 is if C1 equals 0 or this hyperbolic sine function equals 0. Now, we're assuming that L is strictly greater than 0, just based on this inequality right here. So if L is strictly greater than 0, this hyperbolic sine of this positive constant times this positive constant cannot be 0. And if you're saying to yourself, I don't remember that, I don't remember how that works, remember again that the hyperbolic sine function looks like this. It's 1/2 times e to the x minus e to the negative x. So here's 1/2 e to the x, it looks roughly like that. And here's 1/2 e to the negative x, or negative 1/2 e to the negative x, it looks like that. And our hyperbolic sine function looks like this. So the only time the hyperbolic sine function is 0 is when the expression inside, sometimes called the argument, is 0. If that is 0, then we get 0. Otherwise, this is not going to be 0. So if this times this equals 0, And since this isn't 0, that means that C1 must be 0. Now, if C1 is 0 and C2 is 0, that means that F must be 0. But we're looking for eigenfunctions. Again, non-zero solutions of that eigenvalue problem. So we want non-zero solutions to the differential equation that satisfy the boundary conditions. So the only way that lambda could be negative is if F was equal to 0. And since that's not possible, that means that lambda is not negative. Or in other words, the eigenvalue problem has no negative eigenvalues. We could have inferred that, or we did already infer that by looking at the Rayleigh quotient. But again, we don't like to just plug and chug and infer things from there. But from first principles, we can see that lambda being negative doesn't work because it would require us to have a 0 a function f of x equals 0 for an eigenfunction, and that's not possible. It's not the definition, or it's not consistent with the definition of an eigenfunction. Okay, so lambda can't be negative. Now let's look at the second case. Let's look at the case when lambda is just 0. In that case, f double prime plus lambda f equals 0 just simplifies to f double prime equals 0. Now, if I want to find f, I'll just anti-differentiate twice. F prime is the antiderivative of f double prime. In that case, or in this case, that's the antiderivative of 0. Antiderivative of 0 is a constant, because the derivative of a constant is 0. Now we're trying to find f. So we'll anti-differentiate again. The antiderivative of that constant with respect to x is that constant times x. Then we'll add a constant. So that means that f of x is equal to this. If lambda equals 0, this differential equation simplifies to this, and then this would be the general solution to this differential equation. Now, with these problems, we're seeking solutions to the differential equation that satisfy the boundary conditions. So remember, our first boundary condition for this particular example was f of 0 equals 0. If I substitute that in over here, I've got C1 times 0 plus C2, which is just C2. So f of 0 equals C2. We're going to set that equal to 0. So that means that C2 must be 0. Okay. And then we also have that f of L must be 0. So that's C1 times L plus C2, but we already know that that's 0. And that result has to be equal to 0. So after substituting, we set that result equal to 0. And we try to solve for C1. But remember, L is strictly positive, because that's what this says right here. We're on the interval from 0, x equals 0 to x equals L. It's the interval of interest for us. L is to the right of x. So this is positive. So the only way that this product is 0 is if C1 is 0, given our other assumptions. So again, f is the 0 function. But a 0 function can't be an eigenfunction, because eigenfunctions are by definition non-zero solutions to the boundary value problem. So that means that the lambda equals 0 that we used right here is not an eigenvalue. Okay. But again, because we substituted into the Rayleigh quotient and simplified, we knew that. We knew that this was true. We actually already discussed it earlier. So lambda has to be positive. We've already examined what happens when we look at lambda being negative and lambda being 0. So let's see what happens when lambda is strictly positive and see what the eigenvalues and eigenfunctions look like. Okay, so we're dealing with f double prime plus lambda f equals 0. That is a homogeneous, linear, ordinary differential equation with constant coefficients. Now remember from your ordinary differential equations class, to solve that, we let f of x equal e to the mx. You want to differentiate twice. And then you substitute into the differential equation. There's my f double prime plus lambda times f equals 0. And that's equivalent to this. Now the exponential is never 0, so we get this. Now, one thing that I will say is many times professors will skip this step because it's assumed that you remember when you're dealing with a constant coefficient equation that the form of the solution is e to the mx. If you differentiate twice and substitute and then simplify out the e to the mx, you will always get a polynomial equation in m. In this case, that's the parameter I'm choosing to use right here. So you're always going to get this characteristic equation. Many people skip all of those steps that I've just written and just go straight from the differential equation, which is homogeneous with constant coefficients, to this characteristic equation, and then they solve the characteristic equation. I'm totally fine with you doing that, provided that you know where this comes from. Because if you are able to solve this for m, and we will by subtracting lambda from both sides, and then taking the square root, do plus or minus the square root of negative lambda. Remember, lambda is positive, so that's plus or minus the square root of lambda times I. So in that case, remember from your ordinary differential equations class, if you have complex conjugate roots to your characteristic equation, the two linearly independent solutions would be e to the alpha x cosine of beta x and e to the alpha x sine of beta x, the two linearly independent real solutions to the differential equation. So in our case, alpha is 0. Beta is the square root of lambda. And that means that f sub 1 is just cosine of the square root of lambda times x. And f sub 2 is sine. Looks exactly the same, except you change the cosine with a sine. So those would be your two linearly independent solutions to the differential equation, and therefore your general solution, or a form of the general solution, is C1 times cosine of square root of lambda times x plus C2 times sine of square root of lambda times x. So we know that's true. Now, again, you don't have to show all of this. I'm just reviewing it for those students that need to review it. Okay, so we've done that. Now that's a general solution to the differential equation, but we don't want general solutions to the differential equation. We are still seeking eigenfunctions corresponding to eigenvalues, or functions that satisfy the differential equation, call them eigenfunctions, that correspond to particular values of that parameter, which we're calling eigenvalues. And those are functions that not just satisfy the differential equation, I should add that they also satisfy the boundary conditions. In this case, our boundary conditions are f of 0 equals 0, first one. So if I replace x with 0, I get this. Cosine of 0 is 1. Sine of 0 is 0. So we get C1 there. We're going to set that equal to 0. So that means that C1 is equal to 0. And then f of L equals 0 implies the following. So since C1 is equal to 0, I'm just going to leave that term off this time. So I've got 0 plus C2 times sine of the square root of lambda times L. Now this has to be equal to 0. Again, I've got a product. The only way this product equals 0 is if this equals 0 or this equals 0. Now, if C2 equals 0, we'd have a 0 function, and we are not interested in a 0 function. So that means that sine of the square root of lambda times L must be 0. That's the only way. Now, the sine function is 0 infinitely many times. Remember, sine looks like this, and it repeats in both directions indefinitely. There's negative pi, there's 0, there's pi, there's 2 pi, there's 3 pi, and so on. So this will be satisfied, this equation will be satisfied whenever the expression inside the sine function is equal to a multiple of pi. So we would need the square root of lambda times L to be n times pi, where n is an integer. But remember, L is positive and lambda is strictly positive here. So that means we're only interested in the values of n that will give us positive numbers over here. So this is true, or in order for this to be true, and this to be true for the restrictions on lambda and L that are consistent with our eigenvalue problem, then this will be true for n equals 1, 2, 3, and so on. So then we'll divide everything by L. Sorry, my lambda looks like an X. There we go. And we'll square both sides. And those are our eigenvalues. So since we've got a formula involving n, we could call that lambda sub n. So we'll have lambda sub 1 is pi squared over L squared, and lambda sub 2 is 4 times pi squared over L squared, and lambda sub 3 is 9 times pi squared over L squared. Those are the eigenvalues of our regular Sturm-Liouville problem. Now, we're not just interested in finding the eigenvalues. Of course, we were asked to find the eigenfunctions as well. So once you've got your lambda sub n, and you know that C1 is 0, well, you can put the lambda sub n in right here to get the corresponding functions. Now, rather than writing f of x, we'll write f sub n of x, because there are infinitely many of these. So we're going to have C2 times sine of the square root of lambda times x. And of course, we're substituting in n squared lambda, or pi squared over L squared. This is n pi x over L. And we don't really need an arbitrary constant out here, so we'll just choose for that constant to be 1. So that means our eigenfunctions are sine of n pi x over L. For, again, n equals 1, 2, 3, and so on. That was definitely the long form of that solution. I showed you a lot of things that you may have needed to review from previous classes. But I find that many students need to review that stuff. So we'll do that this time and maybe the next time. but then we'll probably stop reviewing as much and just proceed through the method for the other examples of solutions to regular Sturm-Liouville problems. Okay, so let's recap, and I think we'll end this video and then maybe do another example in the next video. I've got a regular Sturm-Liouville problem. We could just take our regular Sturm-Liouville problem, compare it to the general form of a regular Sturm-Liouville problem, identify P, Q, and lambda, and then, or identify P, Q, and sigma, excuse me, and then substitute those values into the Rayleigh quotient. And oops, that's not the right page. When we do that, we end up here. And that gives us a little bit of insight into the eigenvalues for this particular Sturm-Liouville problem. And then we said, okay, we can even go further. We know that this is greater than or equal to 0 because of the form of the Rayleigh quotient, but we also know that lambda will only equal 0 if f prime equals 0. And if f prime equals 0, then f is the 0 function because of our boundary conditions. Therefore, lambda is strictly positive. We could have done all of that using the Rayleigh quotient. But generally, if you're taking a PDE class, that's not what you do. If you're solving a differential equation or a regular Sturm-Liouville problem like this, and again, it's not just, the question doesn't say just solve the problem, it says find the eigenvalues and eigenfunctions of the regular Sturm-Liouville problem. So it suggests that you do all of that, okay? That's what we're asked to do. In that case, we say, okay, lambda is guaranteed to be real because we are dealing with our regular Sturm-Liouville problem because of the result from theorem 3.8. So we just look at the possibilities. If I were to solve this differential equation, the second order differential equation, the form of the solution would tend to change based on whether lambda was positive, negative, or 0. So we look at the three cases separately. In each case, we find a solution. Now, I want you to notice that if you end up with two values of m that are plus and minus the same real constant, rather than using these two exponential functions, we tend to use the hyperbolic sine and hyperbolic cosine functions in differential equations. And again, the reason for that is because when we do, the simplification of the results when we apply the boundary conditions is relatively straightforward because of what we know about the hyperbolic sine and hyperbolic cosine functions. Okay, so we do that, we go case by case. Lambda being negative would give us this combination of hyperbolic sine and hyperbolic cosine functions, which turns out, given our boundary conditions, would correspond to the 0 function, which is not a solution to the, or it's not an eigenfunction of the regular Sturm-Liouville problem. And then next thing we would do is look at the case where lambda equals 0. And in the case of when lambda equals 0, we get this. In that case, that's our solution. And it turns out that given our boundary conditions, we end up with the 0 function again. So we find that lambda equals 0 is not an eigenvalue. Then finally, we look at the third case where lambda is positive. And solving this from first principles using the methods that we studied in ordinary differential equations, we find that our solution involves a linear combination of sine and cosine functions. Given that that's true, these two boundary conditions lead to this. The only solutions to the differential equation that satisfy both of the boundary conditions at the same time are these. Sine of n pi x over L for n equals 1, 2, 3. We've got actually infinitely many solutions to that boundary value problem, and they all look like this. And they correspond to these values of that real parameter lambda. So these are our eigenvalues, and these are our eigenfunctions. There shouldn't be a space there. I accidentally left a space. for this given problem. And I want you to notice those conditions, those results from theorem 3.8, they hold. Theorem 3.8 said that we would have real eigenvalues, and we do. All of those are real numbers. L is a number, n is 1, 2, 3, 4, so you square it, we still get numbers. Multiply by pi squared, these are all real numbers. So we've got infinitely many eigenvalues there. As n increases, lambda sub n increases. As n goes to infinity, lambda sub n goes to infinity. So we've got an increasing sequence. And I want you to notice this as well. And what else? Each of those eigenvalues corresponds to an eigenfunction. So I've got a set of eigenfunctions that looks like this. Now we're guaranteed by theorem 3.8 that those are all, that forms an orthogonal set. So that means they're pairwise orthogonal. So that means for the interval of interest, in the interval, on the interval, excuse me, from 0 to L, if I integrate sine of n pi x over L times sine of m pi x over L, where n and m are different. So I just take two functions from this list, I'm going to get 0. And that's actually a result that we looked at when we studied Fourier series in a different series of videos. Okay, so that was pretty long-winded. I hope the detail helped. If you want something with less detail, we'll look at something with a little less detail in the next video. That's your first example of a solution of a Sturm-Liouville problem.